What's up, AP Statistics? This is Mr. Slagle reporting from the Slagle compound. We're going to get started here with day 3 of density curves and normal distributions. This is the last day of this lesson, and it's the last day of this unit. We're going to start reviewing very soon and try and wrap this up. But make sure I want to. We'll wait till we get back and I check in with you guys first, so don't worry. Okay, let's take a look. Here we have our data from when we reached out and we looked at our wingspans in class. Now, this is interesting data because we want to look. We can talk about comparisons. We can talk about z-scores, but the question is this normally distributed? Is this something that we can look at as normal? And that's really hard to say. Now, if we were just technically, what is this data from? This is from the students of Mr. Slagle's 4th period AP Statistics classroom. It's their wingspans. Now, I think if we were to really measure this and talk about what should be normal, we should not have mixed guys and girls in the same data set. We probably should have looked at them separately. But let's just, for the sake of practicing, let's look at this. We're going to call it all one data set, and then we're gonna go from there. So, is this normally distributed? And this one turns out to be fairly hard to say. But to answer that question, we want to make sure that we have all the tools necessary, and we'll try and come to some sort of an answer towards the end of the video. So I plugged our wingspans into Staplets. I have a dot plot. I have a histogram. I've got a box plot, and I've got the summary statistics up here at the top. Now, the reason we care about whether or not a distribution is normal is because if it's normal, then we can start to make calculations based on the likelihood of certain events happening. If it's normal, then we can use Table A, and we can use normal CDF, and we can start making calculations based on the fact that we know that it's normal. But as we've seen previously, there are plenty of distributions that are not normal, like the uniform one of rolling the dice. Okay, and so if the distribution is not normal, we can't use Table A. We can't use normal CDF. So in this class, it's going to be a common practice that before you're able to make any calculations whatsoever using Table A or normal CDF or inverse normal, before you can do any of those and any of the problems, you have to first convince people that the distribution itself is normal. So if it says it in the problem, you're good, but if it doesn't, then you have to argue it. And that's what you're going to learn today. How do we argue whether or not a data set is normal? So let's go ahead and get started. We're going to come back to this one at the end. So one thing you have to realize is this is what I just said. Once we know a distribution is approximately normal, we are allowed to make statements about the probability of observations occurring, but only once we know, right? We can't use those Table A's. We can't use normal CDF until we know that it's normal. And I already said that. So you can pause the video there. I'm going to keep moving if people need to write. How do we know if our data is normally distributed? Well, there's some characteristics of normal data that we've all learned about, and we can summarize really quickly. The first is, here's my 4-point inspection to determine whether or not a data set is approximately normal. The first thing you should do is look at a histogram, box plot, stem plot, and dot plot. And what you're doing there, you can look at something. You're looking to see if it looks symmetric. Okay, if the data set is skewed, or maybe it has multiple peaks, not even like you can't even just be symmetry, because if it has multiple peaks, if it is skewed, or if it looks like it's some other distribution like the uniform distribution, then you can't use Table A and you can't use normal CDF. It's not a normal distribution. So the first thing we look at is shape. It should have that kind of nice, beautiful bell curve. And if it doesn't, then you can't proceed with normality. Another really quick check for um, whether or not something is normal is look and see how close the mean and median are. If they're pretty close, if they're similar, then there might be some symmetry present. So that's just a quick check. It's not a very in-depth one. Now, if you look at a uniform distribution is symmetric. It is symmetric. It doesn't have any skew, and it doesn't have necessarily multiple individual peaks. It's just flat, a uniform distribution. But the uniform distribution it's not normal because of how the data falls relative to the mean. With a normal distribution, you have this flat line, right? When really 68% of the data should be within one standard deviation. So sometimes you have to check. You have to physically check and look and make sure, oh yeah, this is within one standard deviation, or oh yeah, this is within one standard deviation. Okay. And then all three should be roughly close. So within one standard deviation, you should have roughly 68% of the data. Within two standard deviations, you should have 95% of the data. Within three standard deviations, you should have 99.7, roughly, or close to 100% within three standard deviations. Your max and your min should fall very close to three standard deviations. So yeah, or less than within three standard deviations. Okay, and then the last thing is there's this graph that's new and exciting called a normal probability plot. And I'm going to explain to you what that is, and I'm going to show you how to use it here in just a minute. But before I do, I would like to look back at the graph for our wingspan, and let's do 1 through 3 and just kind of talk about that briefly. Let's go back really quickly. All right, so the first one is check the graph, look for symmetry, look for whether it looks skewed, look for multiple peaks. So if I'm looking at the dot plot, here's our histogram. It looks like we kind of have this kind of bell-shaped curve with a little bit of a bump right here. It looks symmetric in the box plot. We have it looks like a single peak there if we were to drape a blanket over our shape. And then it looks like we have kind of a dense group here in the middle, but maybe not super dense. It's kind of spread out a little bit. So let's take a look. The graph symmetry, it's possible that it's normal. It's quite possible based on symmetry. And I see only one peak here. I see one big cluster, and we have a little bit of variability between 66 and 68. But so the graph, it's believable that it's symmetric. Are the mean and the median similar? Let's take a look. The mean is 67.9, so almost 68, and the median is 68.4. So they're pretty close. Yeah, they're pretty close. So symmetry is plausible. All right, now let's look at the empirical rule. Is roughly 68% of the data within one standard deviation of the mean? So let's go to the mean, and we can do some quick calculations. So let me open up my calculator here, clear, and we're going to do the mean plus the standard deviation, 67.905, plus standard deviation is 4.141. So we're sitting at about, for the standard deviation, the cutoff for one standard deviation, so the way that we could say this is we say x bar plus or minus one standard deviation equals, and we can write this in interval notation. I'm going to do my best here. X bar plus or minus one standard deviation, so plus goes up to 72.046. And let's do it again. Minus down to 63.764. So let's take a look. 72 for one standard deviation is right about there, so in interval notation. And then 63.7, we're looking about, I don't know, roughly right there. And our mean, 67, is somewhere in the middle. So within one standard deviation, we should have 68% of the data. And if we look, we have a total of 28 observations. Within interval 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have 19 out of 28. So 19 out of 28 observations fall. 19 divided by 28 is roughly 0.679. So that's really close. Nice job. Okay. So way to go, Wingspan. Hey, class, I don't mean to alarm you, but you might be normal. Okay, let's go back to green, not pink. Now we can repeat this process. Why don't you guys do that as well? Let's see how many are within 2 standard deviations and 3 standard deviations real quick. And actually, I might pause the video and we'll just get that going. Then you guys can check. All right, we're back. I got this all on to one screen here, and I checked so you guys can check your intervals. But I have little marks on my dot plot. So within 1 standard deviation, we have 0.679 or 67.9% of our data, 19 out of 28 observations, so that's pretty darn exciting. Within 2 standard deviations, we actually have 27. Now, if you do the mean 67.905 minus 2 times 4.141, you're just past the minimum in the green check mark here. So you have a boundary down here. And if you do 67.905 plus 2 times the standard deviation, you're going to be at 76.187, which is just shy of your max, 67.25. So we have 27 to 28 observations that are there, that are within this region, 59.623 and 76.187. And this is how you would show your work. And then within 3 standard deviations, we have our blue lines. We have all of our data, 28 out of 28 observations. So when I'm looking at these, the 68, this is raw data from our class, 68, 95, and 99.7. It looks like this data is pretty normal based on the empirical rule. So that's pretty exciting. And we only really have one more check, and we'll get to that in just a bit. Okay, let's keep going. So we've checked the graph, we looked at the mean and the median, and we looked at the empirical rule. Now, what you are likely to see for a failure in this department is you will have significantly less than 28, significantly less than 68 within 1 standard deviation. So maybe like 50 or something. Or you might have significantly more, like 80% of the data is within 1 standard deviation. If that's the case, it's probably not normally distributed. It might follow some other distribution. So just doing a quick tally mark, there is one question like this on your assignment where you have to actually do those calculations that I just did, count the number of observations within those intervals. Okay, so now let's move on to check number 4. We have our graph, we have checking the mean and median for symmetry, checking the empirical rule to make sure that, the data is clustered how it should be. And now checking this thing called a normal probability plot. So what's a normal probability plot? Well, a normal probability plot is a very interesting plot. So basically, it's a really quick way to determine whether or not something is normally distributed. If the data seems to lie in roughly a straight line on a normal probability plot, then if it's close to a straight line, then the data are approximately normally distributed. And I often misspeak grammar-wise. You're supposed to say the data are, because one data point is called the datum, so data are plural, approximately normally distributed. And if you see a nonlinear pattern in the points, then it indicates something that is non-normal. It's really simple, but there is a little hand waving that goes on because, well, I can see some small deviations here, and I can see some things that are off of that line here, and some deviations here, but for the most part it is pretty much in a straight line. So we're looking at stopwatch times based on the normal probability plot. This is our data from class. The stopwatch times look approximately normally distributed. They're falling in a straight line. But this was supposed to be our normal data. How do we create this on our calculators? Well, it's really easy. You enter the data into a list. You turn on stat plot, second y equals, or it's just second stat plot, which is the top left, which is where we've been going. And you change the graph type to what's on the far right option. It kind of looks like a bunch of points in a line. You press graph and then zoom stat, and you should create a normal probability plot. If you have data in your calculator and you want to take a minute to try that, please do. And for those that don't have the calculator app on your phone, please see if you can get that installed as soon as you can. Talk to someone that does have it installed. Okay. So all we do is look to see if they look like they're in a straight line. Now let's take a look at some other examples. Here's some IQ scores. This is definitely, so there's no line present on this plot. Oh, I forgot to mention, these were made with Staplets. So if you go to Staplets and you enter your data, you can also just do the drop-down menu, but you need to know how to use your calculator because that's what you're allowed on your AP exam. So you need to know this process as well. So here we have some IQ scores. IQ is, and test scores are generally normally distributed. You can see, you know, if all of these fell down, if all of these dots on my plot fell down and hit this axis here, we would have the dots that are present on the IQ dot plot here. And they all do lie in a straight line. So one thing I did not explain is what is a normal probability plot. So let me just, what are we actually graphing here? So on the bottom, we have all of the data. On our horizontal axis, we have all of the data that was collected in one variable. So this is actually univariate, it's a univariate graph. But we have something up here. So what this is it is the expected z-scores that you would see if the data were perfectly normally distributed. So what your calculator does is it says, oh, you have a data set, maybe we have 100 observations here. Should be close to 100. Okay? What the computer does and what your calculator does, it says, oh, you have 100 observations? Well, that means we should see, you know, it kind of applies the empirical rule, but it actually implies it for each individual z-score. So it's saying, like, we should have so much of the data, if it's perfectly normal, that's within this region, and so much of the data that's within this region. So it's not just the empirical rule, it's literally down to the specific z-score for each point. So what it does is it creates a graph, and it says, oh, the x value of each point is we list them all in order, right? The x value of each point is the observed measurement, and then the y value of each point is if in a perfect world, if these 100 data points were perfectly normally distributed, we should expect to see the following z-scores. So it generates the z-scores for those points in a data set of 100. So the y values for any data set of 100 are going to be the same for a normal probability plot. So basically what it does is it says, if it's perfectly normal, these should lie in a straight line, and here's what the z-scores should be, and then you check to see how straight it is. So they're off by a little bit, but it's looking good. Okay, let's keep moving. So yeah, I would say these are normally, IQ is approximately normally distributed. I can see this kind of tight group in the middle. They look linear, and it looks like there's this group of data in the middle, and then it kind of thins out towards the edges out here. That's a good indication that it's normally distributed. So that's great, using the normal probability plot. Approximately normal. We have to say approximately normal because it's not perfectly normal. Otherwise, they would be in a straight line. Let's take a look at this one. Now, when we look at the dot plot here, we can see that this is clearly skewed to the right, skewed towards this where it's being pulled this direction. So what we have in our graph here with a right skew is we have this kind of curve that's going this way. Okay, so you can expect Now, some people actually graph these backwards, so I don't want to say that if it's an arc like this, it's always skewed to the right. But as long as expected z-score is on the y-axis, then we don't really have a line doesn't describe this relationship the best. If you were to kind of follow along, it's not a line that describes it best. It's actually more of a curve. So if you're looking at this data, I would say that this particular data is not approximately normally distributed because of a couple things. Number one, we have this heavy number of points over here on the left, and then it kind of tapers out going this direction. And the other reason is we don't have a linear pattern, approximate linear pattern in the normal probability plot. It's also called, this plot is also called a quantile plot or a QQ plot as well, but normal probability plot is what we're going to call it for the class. So it doesn't look approximately linear, so I would say this is not approximately normal data. It looks like it has an arc to it. And then this one is interesting as well. And here we see, this one's maybe a little bit more extreme. So we have this kind of sweep. Here's the data set. And it looks like, I think with this one, one of the reasons, it's not normal for a couple reasons. The first of which is we have this kind of obvious sway to the data here. Also, we have this like very nonlinear kind of almost an S shape in our normal probability plot. And I think with this data set, if you actually do the calculations, you can look based on the empirical rule that within one standard deviation, there's like 80% of the data if you were to actually sit down and do the calculations. Or, if I gave you you'd be able to see it clearly. All right, so this is not normal. I'm going to show you some examples. This is not approximately normal because of the nonlinear pattern present and the fact that you have a lot of data points within one standard deviation. This one is not normal because it is skewed to the right, and we have a bulk of the data points over on one side. If you can imagine these falling down onto our graph down this direction and landing and stacking on top of each other, you would get the shape of your distribution. And this is not normal because we have an obvious kind of a nonlinear or arc pattern in our data. All right, now here's what I want you guys to think. Which of these are from normal distributions, if any? And let me know what you think. You can pause the video, you can discuss. It shouldn't take too long. Yeah, I'm going to start explaining, so better go for it. So it turns out with this one is all three of these are from a normal distribution. So how they were created is we took a normal distribution of data and we randomly selected an item or 20 items from that distribution. And so all of these are from a perfectly normal distribution. And the reason I'm showing you this is to show you what you can expect to see in wiggles and samples. So this is from a perfectly normal distribution, and these are perfectly normal wiggles if you're sampling and resampling from that normal distribution. So this is the amount of non-linearity that you should be able to stomach to say, oh yeah, it's believable that these come from a normal distribution. So I wanted you guys to see, like, are they all supposed to be perfectly straight? No, you should have a little bit of wiggling going on. And remember, your reasoning is kind of, you're going to say one of these two things when you interpret your normal probability plot. Okay. It's believable. These all look like follow a pretty much a linear pattern, so we can assume that the data from which it's selected is approximately normal. All right, now let's look at our class data that we had. Here's our dice rolls, which we know to be uniform data. And we can see very clearly a couple in the normal probability plot. We can see a couple ways that this is not, I would say this is non-normal. It's non-normal because you can see kind of a sway in the data, number one. You can see this kind of curve in the data. That's the first thing. The second thing is you shouldn't have large amounts of data out in the tails like this. This should not happen for this to be non-normal. So this is non-normal, not even just because it's non-linear, but because we have these large sums of data out towards the edge of our data set. So I can clearly see from the amount of points present here that our data is not going to fall. The empirical rule is not going to be helpful for us here. Things are spread way too far spread out in the tails for this to be normal data. Also, we have fairly a large set of deviations from the line right here and right here. So we have these large deviations, lots of data points that are not in line is another telltale sign of this being non-normal. Okay, here's our penny distance, which we know to be skewed. We were tossing the penny at the target, and some of them ended up rolling. And so this is what you should expect to see when you have a skew to the right. So how do you read this and know that it's right skewed and not left skewed? Again, imagine all of these data points falling directly down, like so. This is non-normal because we have an obvious curve to our data here that's not following a linear pattern. And also, if these data points were to fall down onto our horizontal axis here, we would see a large cluster of them over on the left. We would create our dot plot, and then few of them over here, which means we're skewed to the right. So what would left skewed look like? Pause the video and take a minute to draw that. You would expect left skewed to look something like this. You have your line, and then that would predict, and you'd have some points like this, and then you would see this steep upward curve with lots of dots, like so. Sorry, I just broke my computer. Like this. So you'd have all these dots over here, and if these were to fall down onto the axis, then we would see a large collection of dots, and it would thin out over on the left. So this would be left skewed. This is right skewed. So for those, if it's arcing and opening down, and your expected z-scores on the y-axis, this is skewed to the right. If it's opening up like this and it's making like a cup pattern, then we are going to be skewed to the left. Oops. There we go. All right, we're back to wingspan. I didn't show you the normal probability plot. Does it appear that these fall in an approximately normal pattern? So it passed based on the histogram. It looked like it had a single peak. It looked fairly symmetric with the dot plot. This is our wingspans from class. The mean and median were very close. We checked the empirical rule, and the data fell pretty well. And then now we have this beautiful normal probability plot, and they look to me like we have some slight deviations from the mean, slight deviations from the line here, but nothing too extreme. This is within reason, thinking back to those 3 examples that we looked at right here. It's pretty standard to see some deviations that look like that. So if you want to see a textbook response to what this might look like on an AP exam or a free response question, researchers recorded the survival times in days of 72 guinea pigs after they were injected with infectious bacteria in a medical experiment. These people are cruel. A normal probability plot of data is shown. Use the graph to determine if the distribution of survival times is approximately normal. I should have had a very cute picture of a guinea pig with their eyes bulging right there. It's my mistake. So here we see this, curve down. So the textbook answer that we would, the perfect answer to something like this, you guys can go ahead and try to respond. But this is what you should expect to see. The normal probability plot is clearly curved, indicating that the distribution of survival time for the 72 guinea pigs is not approximately normal. Okay. You also could have added in your answer, it is apparent that there is a large cluster of points and in a vertical pattern on the left, indicating that this is skewed to the right and is that the distribution of survival time for the 72 guinea pigs is not normal. Thanks for watching the video today. I hope that was helpful. Your homework is posted, and solutions are posted as well. And hope you're having a great time, and I'll be back soon.